So, hey everyone, good afternoon. So last time I briefly introduced about this lecture, this class, and I defined what propositions are, and I showed a couple of examples here. And I also defined some operations between the propositions. So the first example was negation, and the second operation was called AND. So conjunction is also called AND operation. And there are two different types of OR operations. The first one is called the disjunction, or also called the inclusive OR. So in this case, this P or Q is true if at least one of them is true. And the second one is called the exclusive OR, or XOR shortly. In this case, XOR of propositions P and Q is true if and only if exactly one of them is true. So if both are true, then P XOR Q is false. So for example, you could say, in the case of inclusive OR, so in English, we use this term OR for this both meaning. It could mean inclusive or exclusive OR. When you say you can take this course or this course, in this case, it means that you can take both class or at least one of them. But if we say soup or salad comes with entry, then we usually don't expect to get both soup and salad, but we'll get exactly one of them. So that's called the exclusive OR. And today we are start from the implication. So implication is denoted by this arrow symbol. So, and it is read by if P, then Q. So this implication proposition is false when P is true and Q is false, and otherwise is true. So if you look at this truth table, you can see that there are three truths here and only one false. And this implication is also for the conditional statement, and this P then, if P then Q can be written as P implies Q, or P only if Q, or P is sufficient condition for Q, or Q is necessary condition for Q. So for example, let's say let P and Q be the two propositions. P is I'm elected, and Q is I owe lower taxes. So the proposition if P then Q is that if I'm elected, then I owe lower taxes. So if I'm not elected, then P is false, so that if P then Q is always true, no matter if Q is true or false. And if I'm elected, then this proposition is true only if and only if Q is true. So it means that if a politician was lying, if he gets elected and does not lower tax, but even if he doesn't lower the tax, he's not lying if he doesn't get elected. So that's what the implication proposition says. So there are some other propositions which can be defined from the implication. So for example, converse of this implication is if Q then P. And we can also define contrapositive and inverse as described in this slide. And we see later that this contrapositive of an implication has exactly the same truth value as the original proposition. So we could say this contrapositive and the original implication are logically equivalent. So the final operation is called biconditional. So biconditional is read P if and only if Q. So it is true when P and Q have exactly the same truth value. And this is first authorized. So you can see that this proposition is true if both P and Q are true or both are false. And we can also say, we can sometimes read it as a P if of Q or P is necessary and sufficient condition for Q. So when you combine different types of operation, of course, the naive way to determine the order of operation is to put some bracket symbol like this. But we always want to simplify the formulas and equations. So we use bracket only when it is necessary. Otherwise, we just omit this bracket. So there's 5 operators here, and you can see that which operation should be taken first or not, or later. So for example, in this position, you don't need actually any bracket. You can simply write like this. These two left and right propositions are the same proposition. And in the second one, so this negation should be taken first. And then between this or and operation, this or operation should be taken first. So you get this one. So as I mentioned last time, we can construct some more complicated propositions using some simpler ones. So by combining them using logical operations. So, and you can construct a truth table for such a compound proposition. So usually there are some atomic propositions. So for example, in this example compound proposition, you can find this P and Q, which are atomic propositions. So you basically write P and Q on the left side, and you also so the number of rows is 2 to the power of the number of atomic propositions. So there are 4 combinations of propositions P and Q. So you see that true, 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 first, true, and first and first. And when you compute the truth table of this proposition, you just you can need some building blocks, truth tables of some building blocks. So for example, you can see negation of P here, and then negation of P and the Q, and so on. So you can, for example, combine them to generate a truth table of this compound proposition. And by the way, you can observe that this final compound proposition is actually simply equivalent to Q. It doesn't depend on the truth value of P. Okay, so I've already used these terms several times, but let me here formally define what logical equivalence means. So we use this notation here, and we say propositions P and Q are logically equivalent if their truth table are identical. So for example, an implication is equivalent to its contrapositive, but the converse is not, doesn't necessarily have to be equivalent to the original implication. And you can simply check this fact by building a truth table. Okay, so another definition, another terms. I will introduce 3 terms here, but I mostly use this term tautology in the rest of slides. And I barely use other terms, contradiction or contingency. So a proposition is called a tautology if it's always true. So meaning that its truth table contains only two values. There's no false. And contradiction is a proposition which is always false. So you can say that contradiction, the negation of a contradiction is a tautology. And contingency is a proposition which is neither a tautology or nor a contradiction. So the typical example of tautology is P or negation P, P or not P, because if P is true, then this one is true. P is true, so the whole proposition is true. And if P is false, then not P is true, so this proposition is anyway true. And there are two typical examples of contradictions here. So here's one example of a propositional equivalence. You can see that these two compound propositions are logically equivalent. So these two propositions are true only when both P and Q are false, otherwise false. So you can use this notation. Oops. Not P or Q is logically equivalent to not P and not Q. And one application is that when you think of the negation of this proposition, bypass a cell phone or a computer, let's say let P denote the proposition bypass a cell phone, and Q is the proposition that bypass a computer. And when you want to express the negation of this proposition is P and Q. So the negation of this proposition is equivalent to not P or not Q, as we observed above. And if we translate this proposition into English, then it will become bypass no cell phone or no computer. In fact, this is called De Morgan's law, and I'll show you later. Okay. So when you show the propositional equivalences between different propositions, the most naive way, but the simplest way to show this fact is to simply build the truth tables of these propositions. So here you can see that there are three atomic propositions, P, Q, and R. So if you build a truth table, this truth table would have 8 rows. So the all possible combinations of P, Q, and R. So from TTT to FFF, there are 8 combinations here. And based on this truth value of P, Q, and R, you can just fill the rest of the truth table. So for example, when you compute the truth value of Q and R, you can ignore first column, but you can use the second and third column to compute this AND operation and so on. And you can see that these two red propositions are totally identical. These are true for the first 5 rows, and these propositions are false for the final 3 truth values. So there are some important logical equivalences here. So the first 2 equivalences are called De Morgan's law. So this is a De Morgan's law for AND operation, and the second one is De Morgan's law for OR operation. So it is very easy to show these equivalences by simply building truth values. So you can just check them by yourself. So one important law is for the associativity law. So here, P and Q and R is equivalent to P and Q and R. So you can just change the order of operations between these propositions when you take two AND operation between three propositions. And the same is true for the inclusive OR operation. So this is called the associativity law for AND operation. So you can simply write this proposition like this because we already showed that these two propositions are logically equivalent. So the order doesn't really matter. So you can simply omit this unnecessary bracket symbol and write P and Q and R like this. So more generally, we can extend this associativity laws for multiple variables. So suppose that there are n propositions denoted by Pn, P1, P2 to Pn, and you can simply write this proposition like this because the order of operation is really doesn't matter, as I mentioned. So for example, when you have four atomic propositions, this proposition and these propositions are logically equivalent, so it doesn't really matter. So that's why we can use this symbol, big end symbol, to denote this end proposition of n propositions. And the same applies for OR operation. And here's the extended De Morgan's law. So, so the previous one was De Morgan's law for two propositions, and you can easily extend these laws for multiple propositions. And of course, if you write a truth table for these two propositions, they would have 2 to the n laws because there are n atomic propositions, but still it is easy to see that only one of these 2 to the n laws has a different value from others. So it is still very easy to show that these two truth tables of these two propositions are the same. And here are some more logical equivalences. And as I mentioned, implication is equivalent to its contrapositive. And you can somehow switch between its implication and or operations using these logical equivalences. And let's see. And let's pick this one and let's see what does it mean. So this proposition is if P then Q, and this proposition is if P then R. So if these two propositions are both true, then if P, then both Q and R are true, because we have a AND operation here. So this proposition, compound proposition, is equivalent to this one. So you can again show this more formally by building a truth table, these two propositions. And also, of course, it is very expensive to already build the truth tables for every single proposition. So sometimes we show that two expressions are logically equivalent by developing a series of logically equivalent statements. So for example, when you'd like to show that this P and Q are logically equivalent, then you can somehow find the sequence of propositions from P1 to Pn such that P is equivalent to P1 and Pk is equivalent to Pk plus 1 for Rk, and Pn is equivalent to Q, to show that P is logically equivalent to Q. So, okay, so another definition. So a compound proposition is called a satisfiable if there is a assignment of truth values to its variable that makes it true. So what does it mean? So let's take this proposition as an example. So there are eight combinations of atomic propositions here. And you can see that if P, Q, and R are all true, then we see that this proposition is also true. So n is one. So we already found one combination of P, Q, and R satisfying, which makes this proposition true. So in this case, this compound proposition is called a satisfiable because there is n is one combination of P, Q, and R, which makes it true. And if there's no such assignment exists, then this compound proposition is called unsatisfiable. So you can easily show that it is very direct from the definition that compound proposition is unsatisfiable, and if and only if its negation is a tautology. Because if proposition is unsatisfiable, meaning that its truth value is always false, no matter the value of atomic propositions. So its negation is always true, which is called a tautology. So let's see one example here. So the following compound proposition is satisfiable. So to show that this proposition is satisfiable, what we have to do is just find one assignment of truth values for P, Q, and R. So one naive way is to try eight possible combinations assignments, but it takes too much time. So we can do it more. We can do it like this. So this proposition is true when these all propositions are true. And how can you find this? Is that if you read this proposition, then this is end proposition basically, end operation of these three building blocks. And first proposition is P or not Q. So either P is true or Q is false. And the same applies for second and third term. So you can easily check that if P, Q, and R are all true, then this is true, this is true, this is true. And you have only OR operation here. So the whole building block becomes true. So the end of these three propositions become also true. And there is, in fact, another assignment which makes it true again. So for example, the same is satisfied when P, Q, and R are false. If these three propositions are all false, then in this time, it's not Q, not R, and not P are all true. So which make this statement and this proposition again true. So there are two possible assignments which make this proposition true. And this is another example of an untestable proposition. Again, this consists of three atomic propositions, P, Q, and R. So if you'd like to show that this proposition is unsatisfiable, you can either build a truth table or you can find more smart way. So here, let me introduce one easy way to show this proposition is unsatisfiable or is false. So first, let's look at this first part, which is same as the previous example here. So if the whole proposition is true, then of course this first part should be also true. And if this is true, and this first proposition is true if and only if these three propositions have the same truth value. So if they are all true or they are all false. But if they are all true, then and now let's look at this one. So if they are all true, then not P, not Q, not R, they are all false. And this building block becomes, this proposition becomes false. Otherwise, if P, Q, R are all true, then, sorry, if P, Q, R are all false, then this one becomes false, and the whole proposition becomes again false. So we can deduce that this whole proposition is always has the first truth value, meaning that this proposition is unsatisfiable. Oh, sorry, I think I missed some questions. So please please do not use direct message, but write a public chat when you ask a question. So first question was, if a compound proposition is unsatisfiable, it's a contradiction. Yeah, that's the same term. So these are, a proposition is contradiction if and only if it is unsatisfiable. Oh, again, the same condition. And if and only if, so if and only if it's just another representation of this biconditional. So you can either use this symbol or just use if and only if. Okay, so the problem of deciding whether a proposition is satisfiable or not has a very long history. So it's one of the most fundamental problems in computer science, and it is known as a Boolean satisfiability problem, and it is simply denoted by SAT. So of course, the SAT problem can be solved by constructing a truth table for given compound proposition. But the problem is that if a compound proposition has n variables, then there would be 2 to the n rows in the truth table. So, so meaning that if your compound proposition has a 20 atomic propositions, P1 to P20, if you somehow build a proposition using these 20 propositions, then let's say the number of rows in the truth table of P would be 2 to the power of 20, which is even larger than 1 million. So it's a huge size. So the problem is, unfortunately, there's no known efficient algorithm solving the SST problem. So the complexity of SST problem is 2 to the n in the worst case. But fortunately, it does, in practice, this problem can be solved very quickly. I mean, not always, but mostly. So in practice, we, in fact, when we solve some computational problems in combinatorics, we can sometimes represent this problem as a SAT problem and use a SAT solver. So there are very well-known, high-quality, popular libraries which efficiently solve the SAT problems. But of course, there are some instances which is not easily solved by such a solver. So in worst case, it could take 2 to the n time, but in average case, it could be very fast. So for example, when you solve some problems from graph theory, let's say shortest path problem, you can represent the shortest path problem using this SAT problem. Or in fact, any MP problem can be represented as SAT problem. Later, if we have some time, then I may introduce what MP means. So you may have heard of 7 millennium mathematical problems, which is known to be the most difficult ways to make $1 million. So one of these 7 problems is what's called P versus MP problem. So, and this SAT is one of the MP complete problem. So let's look at another example, Sudoku. So Sudoku is a puzzle which is represented by 9 times 9 grid made up of 9 3 times 3 subgrids known as blocks. So this one is block and this one is another block. And there are 81 cells in total. So these 81 cells will be assigned one of the numbers from 1 to 9. So how can you solve this puzzle? So what you have to do is basically assign numbers to each blank cell so that every row, every single row, and every column, and every block, every 3 times 3 subgrids contains exactly one to 19. So each of the 9 possible numbers. So this is an example of Sudoku. So in fact, we can represent this Sudoku puzzle using, so we can encode this Sudoku puzzle into SAT problem. So let's say we define this proposition P of P indexed by I, J, and N. So I, J, and N range from 1 to 9. So we say, so this proposition is saying that the cell in row I and column J, so cell I comma J has value. And this is denoted by the proposition P over I, J, and N. So how many propositions do we have? There are 9 cubic propositions here because the range of I, J, and N are from 1 to 9. So which is 729 in total. Yeah. So now we are going to represent some rules of Sudoku using the SAT problem. So here, there are some rules here. For example, every row contains each of the 9 possible numbers. How can you represent this condition using SAT? So this is the answer. The reason is that every row contains every number. So every row means, so row I represented by this I. So first, this AND operation represents every row. And also, and in each row, every number should be contained in at least one cell. So meaning that for every n, so n is from 1 to 9. So n should be assigned to at least one cell in the ith row. So meaning that if the cell in row I and column J has the value n, then this proposition will be true. So meaning that, so if one is contained at least one cell, then at least one of 9 propositions here. So let's say pi 1, 1. We are looking this I 9, 1. So this is true if 1 is contained in cell I1, and this is true if number 1 is contained in the cell I, and since every row should contain every number, 1 should be contained in one of these 9 cells, meaning that at least one of these propositions should be true. So to represent this proposition, we use this OR operation because we just need at least one proposition is true. And this proposition should be true for all n from 1 to 9. So here we use AND operation. And again, this proposition is again should be true for all rows from 1 to 9. So we again have another AND operation here. So please try at home how to, so try it by yourself, represent these other conditions using the step problem. So every column contains every number from 1 to 9. So probably the second one will have very similar form as the first condition, but the third and fourth condition will be a little bit different. Okay, so how can you solve the Sudoku puzzle? So as I mentioned, there are 792 propositions here, which is either true or false. And in the initial state, we are given some conditions. So for example, number 2 is here, meaning that P1, 2, 2 is true. So some values are already assigned. So what you're going to do is to given these truth values, assign the truth values and the conditions of a Sudoku puzzle, we would like to find an assignment which satisfies the previous SAT problem. So the Sudoku puzzle can be converted into such a SAT problem. But the problem is that since there are 729 variables, building a truth table for such a Sudoku puzzle is very infeasible because there are 2 to the 729 rows in the Sudoku table. Of course, since there are some values assigned, we can somehow reduce the number in the exponent, but still it's a very huge value. So in the modern computer science, we say that 2 to the, let's say, computation of something like 2 to the 40 is can be done very fast. 2 to the 60 is kind of a doable. 2 to the 80 is kind of feasible. So if you collect all computing power in the world, then you can solve some problem of complexity 2 to the 80, kind of, but still 2 to the 128 is believed to be infeasible. So this is too large number to be computed. So definitely this value is out of our ability to compute. Oh, thank you. Thank you for asking and answering the question. Okay, another question. I don't understand your question. What does the iteration mean? So there are n propositions, but there are 2 to the n possibilities. So we search for all possible assignment values, but there are 2 to the n possible combinations. Sorry. You mean in the previous slide? So, okay. So what I am doing here is that n is contained in the ice law. Okay. In a cell of the ice law. So this is the proposition I want to represent. So question was about here we are so the question was about this proposition. So question was why do we have a n variable here first instead of having j here first and then n next in the OR operation. So my answer would be there could be, okay, so what I'm explaining here is that how to I found this representation, but it is also true that there are multiple representation, different representation of propositions which are describing the same condition. So you may come up with a totally different proposition which has exactly the same truth table describing this condition. So I would say this is not the only correct answer, but one of the correct answer. And what I tried to express here was that n is contained in a cell of the ice law, which is represented by this OR operation, and that should be iterated from n equals 1 to 9. Okay, thank you for asking. Okay, so I said this truth table is too large to be computed. And of course, there has been a lot of researches to develop much more efficient algorithms for Sudoku. But as I said, SAT problem takes 2 to the n time in the worst case. And one interesting fact is that there are some NP complete problems which may have a great impact in real life. So you could say if you come up with a fast Sudoku solver, that can be used to like accelerate image processing or find a new medicine to cure rare diseases. So these problems come from very different domains, but they are somehow all connected. Okay, so now let's move to the next section. So now in this section, we will study predicate logic. And motivation was that so far we have studied propositional logic, but which is definitely not enough. So here's one example. So all men are mortal, and Socrates is a man. And of course, we know that. So then we can conclude that Socrates is mortal. But this argument is not covered by propositional logic we have studied so far. So this type of argument cannot be represented in propositional logic. So we are going to introduce a new language that talks about objects and properties. So in this predicate logic, we will use some what's called variables, which are usually denoted by lower cases letters X, Y, Z, for example. And we also use what's called a predicate, denoted by these uppercase letters. And quantifiers will be defined later, very soon. So, okay, so what's the predicate? So let's say Px, let Px be the statement x is greater than 3. And this is not a proposition. The reason is that the definition of proposition was that the proposition should be a declarative statement that is either true or false. So a proposition cannot be false and true at the same time. But the P of X is neither true or false, depending on the value of X. So for example, okay. So for example, if X is 4, then this statement is true, but otherwise, if X is 2, then this is false. So that's why this P of X is not a proposition yet. So instead, this is called the predicate, and X is variable. So P of X is called a propositional function P at X. So I remark that propositional function is not a proposition, but it returns a proposition when a specific value is assigned to a variable. So imagine when you think of a function, if you think of let's say function from real numbers to real numbers, function itself is not a real number, right? Function is just a function. You get a real number when you evaluate a certain value at this function. So function returns a real value, but the function is not a real value. So the similar notion is applied here. So the propositional function is not a proposition, but it becomes a proposition when a specific value is assigned to the value of x. So for example, P of x was not the proposition, but the P of 4, for example, is a proposition. Because if you assign 4 here, then this proposition becomes 4 is greater than 3. Now it's a proposition, right? And otherwise, if you assign 2, 2 is greater than 3. It's another proposition you can think of. And also note that the first proposition is true and the second one is false. So this propositional function may return true proposition or false proposition depending on the value of this variable. And also I didn't explain or introduce the notion of domain, but the domain is usually denoted by U, universe. And in this example, I use the set of integers Z as a domain. So this domain sometimes matters very much. Let's see again later in the following slide. And we can also build a compound proposition by combining these propositions from predicate propositional function. So let's say P3, P minus 1 are both propositions. So we can take a OR operation between them. And so these are OR implications. These are all propositions which can be true or false. And also this propositional function may have more than one variables. So for example, in this example, this Rxyz has 3 variables denoted by xyz. And when you assign a value, you should assign 3 values for all variables, x, y, and z. So R1 to 3 is true, and R111 is false. So for example, if you assign only 2 values, let's consider 1 to z. So this is a statement that 1 plus 2 equals z. This is not a proposition because still there's one variable remaining here. So this is still a propositional function, so which becomes a proposition when the value of z is determined. Okay, so now we are going to introduce two quantifiers. So the first one is what's called a universal quantifier. So the universal quantifier quantification can be used in some statements like P of x is true for all values of x in the domain. And Px was not a proposition, but this whole statement can be a proposition, and which is denoted by this symbol. And we usually read it as for all. And this symbol is called a universal quantifier. And here domain is very important. So domain is the set U of all values that we allow x to take. And this type of statement can be true or false depending on the choice of this universe U, depending on the choice of domain. Let's say, consider the statement x squared is not smaller than 0 for all real numbers x. We can write this statement as like this. And now this is a proposition where, let's say, where the domain is the set of real numbers. So you can say, you can write this proposition like this, or you can also write like this to represent that the domain is R. And this statement is of course true because every square, the square of any real value cannot be negative. And this for R can be expressed in various ways in just a plain English. For example, for each for any for arbitrarily given any, these have all the same meaning. Okay, so now this statement is a proposition. So this and proposition is true or false, right? So how can you determine if a certain proposition is true or false? So to show that this proposition is true, we have to show that P of x is true for every element x in the domain. So this is how to show that this statement is true. And otherwise, this statement becomes false if there is at least one element x in the domain such that P of x is false. Because this statement is basically claiming that Px is true for every element x. So only one exception makes this statement false. And element x such that which makes this P of x false is called a counterexample of this statement. Let's take a look at this example. So let's say Qx, let Qx be the statement x is less than 2. And consider the proposition that Qx for all x. And what is the truth value of this where the domain is R? So of course this is false because Q3 is false. And here we use the 3 as a counterexample. And as I briefly mentioned earlier, this domain is very important. when we use these quantifiers, because let's look at this proposition for all x, x squared is equal or greater than x. This statement is true if the domain is the set of integers, because this condition is held when x is an integer. But this statement becomes false if the domain is the set of all real numbers. Can anyone say any counterexample for this one? Okay, great. So 1/2 is one example. Yeah. This is a good counterexample, but 2 cannot be a counterexample for this statement because 2 actually satisfies this condition. Yeah, any number between 0 and 2 will be a counterexample for this proposition. Okay, and there are 2 different types of quantifiers. The first one was a universal, and the second one is what's called the existential quantifier. And we use this quantifier when we say there exists an element x in the domain satisfying some condition. And this is denoted by like this. This is called the existential quantifier. And the whole proposition is written like this. So it means that there is an element, there exists an element x such that p of x is true. Yeah, there is at least one x such that p of x, or for some x, p of x is true. So this statement is true if at least, yeah, literally at least one x satisfies this this condition, p of x. Otherwise, false if p of x is false for every x in the domain. So again, the domain is very important. So let's consider the one example that, oh, sorry. Okay, here's a, sorry. Let me define one more quantifier. So this is not third quantifier, but a simple variant of the second existential quantifier. So it's called a uniqueness quantifier. We just add a screamer here to denote the uniqueness. So when we use this symbol, when we state like there exists a unique element x in the domain such that p of x is true. So we denote by like this. And let's see if this statement, if this proposition is true or not. So first of all, if domain is Q, Q is the set of rational numbers. This proposition is saying that there exists one and only one element in the set of rational elements satisfying x squared is equal to 2. So this is false because there's no such element in Q. So if you compute the square of a rational number, it never becomes true. And if the domain is the set of real numbers, this proposition is still false. Why? Because there are 2 elements satisfying this condition. There are 2 elements plus minus square root of 2 satisfying this condition. So this proposition can be true if you simply if you simply write existence quantifier, then now this proposition becomes true when the domain is the set of real numbers. because it doesn't matter how many elements satisfy this condition, but it is important that at least one element satisfies this condition. So this is true, but this is false. And finally, if the domain is the set of positive real numbers, then now this proposition becomes true because there exists one and only one element, which is the square root of 2, satisfying this condition. And sometimes we use some abbreviated notation together with quantifiers, such as x is less than 0 or x is positive and so on, to restrict the domain of a quantifier. So in this notation, this condition should be satisfied. So let's say there are 4 examples here. Let's say domain is the set of real numbers in this slide. And let's see the first example. So for r x less than 0, x squared is larger than 0. Means for every real number x with x less than 0, x squared is positive. So it is, yeah. So for every negative real number x, x squared is a real number. It's a positive real number. So this proposition is true. And the second one is that for every real number y with non-zero element y cubic is non-zero. So when we use this universal quantifier, this is in fact equivalent to the following representation for or x. If x is negative, then x squared is positive. These two propositions are logically equivalent. And the same applies to the second example. So this is equivalent to for every real number y. If y is non-zero, then the cube of y is also non-zero. So this is equivalent. These are equivalent representation. And in the existence quantifier, you should find the element in the domain satisfying this condition and this condition. So it means that there exists a positive real number z such that z squared is equal to 2. So this is equivalent to exists z such that z is positive and z squared is 2. So here we use the implication, but here we use AND operation. So okay, let's look at the final example. So this one is also this one means this. So exists x such that x is positive and the cube of x is equal to -2. So this statement is false because for every positive x, the cube of x is also positive, so there's no such an element. But I want to point out that different from universal quantifier, these two statements are different. So this restricted domain doesn't mean this. And in fact, this statement is true. Can anyone say why? Why this statement is true? Yeah, right. So in this existence quantifier, we just need to show that there exists at least one element x satisfying this condition. And this is an implication, meaning that if this is first, then this implication becomes true. So if x is negative, let's say -1, then the proposition inside of this existential quantifier becomes true. So that's why this whole proposition becomes true. Okay. Oops. Okay. What happened? Error. I think something is wrong with the slide. Sorry for the trouble. Did this? I think something is missing. Let me reopen. Okay. Sorry for the trouble. So, okay, so these quantifiers have a higher pretenses than or other logical operators. So, meaning that you should take these quantifiers first in the compound proposition. And so, for instance, so for our xpx or qx means this proposition, not this one. But in fact, this is a really bad example of constructing compound proposition. In fact, this is not even a proposition because x in this term is a variable, but we already used this universal quantifier. So this left-hand side has become a proposition. But this q of x is variable, doesn't have an assigned value. So q of x is not yet a proposition. So this whole statement is not yet a proposition, but just still a propositional function. But more seriously, mathematicians never use the same symbol like this. So it would better to, let's say, use for or y, pure y, qx to avoid confusion. And can be considered as a propositional function over variable x. And this is a proposition which can be true or false. So don't use the same symbol like this because it could be very confusing. So sorry, I think I missed the one question. So so this is not a proposition, but you should put universal or existential quantifier in front of this because this is x plus 1. So if you write p of x is a statement that x plus 1 is larger than x, then this is not yet a proposition, but you should write like this, something like this. Then it becomes a proposition. Okay, so similar to compound propositions, we say these two statements involving predicate or quantifiers are logically equivalent if they have exactly the same truth value, no matter which predicate are substituted into these statements, and no matter which domain is used. And we use this equivalence symbol to indicate two such statements are equivalent. So let's say, for example, this is one example. So for all x, p of x and q of x is true if and only if for all x, p of x is true, and for all x, q of x is true. So these two statements are logically equivalent. And the second example is that let's say for all x, not p is true, but this not p is equivalent to p. So these are all equivalent also. So this is a quick proof of the first lemma, first example. So you can show that this statement, this proposition is true only if and only if this one is true. So if this proposition is true, meaning that P of A and Q of A is true for all A in the domain. So, and this is, sorry, I used two different notation in the same slide. I use U in general to denote the domain. So this is true if and only if P of A and Q of A is true for A in the domain, which is equivalent that P of A and Q of A are true. And which is equivalent to the statements that for every x, P of x is true, and for every x, Q of x is true, which is represented by this AND operation. And when you compute the negation of quantifiers, let's consider the one example statement. Every student in your class has taken calculus. So it can be written for every x, P of x, where P of x is a statement that x has taken a course in calculus, and the domain is class. So the negation of this original statement can be written as not for or x, P of x. But you can see that this is actually equivalent to this statement. So there is a student in your class who hasn't taken a course in calculus. And if you convert this plain English into logical statement, we use this representation. So we can say the negation of this universal quantifier is a existential quantifier used with this negation of the internal proposition. And there's another example of about the negation of existential quantifier. You can just take a look at this example. So this is called De Morgan's law for quantifiers. So basically, you can just put this negation inside of this quantifier while switching the type of quantifiers in front of this variable. So if something doesn't, if something is not, something doesn't hold for all elements, meaning that there exists and it's one element X which doesn't satisfy the condition. So this is how to prove. So this is a proof of De Morgan's law. So we show that these two statements are equivalent. So if this is true, if and only if this statement is false, based on the definition of the negation, meaning that there exists A such that P of A is false, which is equivalent to say not P is true, which can be represented like this. And you can make the same argument for the second De Morgan's law. Okay. What time is it? What? Oh, sorry. I didn't realize that it's already 4:47. Let me stop here and stop recording.